Hey, what's up, guys? Hope everybody's doing good. I am here in our home away from home chemistry lab, and I missed you guys so much. I just had to come in here and be with you. I even threw on the old lab coat. I'm gonna put some goggles on here in a minute. But no, seriously, I'm going to be talking about reaction types today, so I wanted to come in here so I can get some chemicals out and actually show you some examples of what I'm talking about. Before we get started, I hope you see what's on the screen here. Disclaimer, we're going to be talking about a lot of stuff. Hopefully this video is not too long, but there is a lot of material to cover, so I want you to chunk it into two parts. Part one is going to be the first three reactions that we talk about, and part two is going to be the last two reactions. So I'll let you know when that is. Okay, so after the third reaction, just kind of stop, process that, maybe do some practice, and then come back and watch the second half. Okay, so we're going to jump right in. This topic kind of piggybacks what we talked about last week about the building chemical equations. We had to learn how to build and balance those chemical equations before we got to these reaction types. So we're going to look at the reaction types. There's 5 basic reaction types. We're going to take them one at a time, starting with the first one. First one we call a synthesis reaction. And obviously the root word there is synthesize. So anytime something is synthesized, it's being made, it's being constructed. So that's what you need to think about with synthesis reactions. We define a synthesis reaction as the reaction between two reactants, and they react to produce a single product. And we also have some other names that we see the synthesis reaction called. It's often referred to as a combination reaction because things are being combined, or a composition reaction because a single product is being composed. And as I already said, think about the process of building up. We're constructing something in a synthesis reaction, and that building up is coming from multiple simpler substances, and those simpler things are being combined to form a more complex product. This type of reaction is the easiest to pick out because there's going to be a single product at the end of the reaction. And as we talk about these reaction types, you're going to see this phrase general form, and that's kind of like a standard template for these reactions. So for example, the general form for a synthesis reaction is A, that could be any element, so just A, plus B, any other element, equals AB, and then as a compound. So element A plus element B equals compound AB. So some ways that we will see this reaction, and I want to do examples so this will gel together. As I already mentioned, you might have something like element A plus element B coming together to form a compound, AB. Sometimes, though, you might have an element, and it's going to be combining with a simple compound, compound BC, to form a more complex compound, compound ABC. So it's just a larger compound. But notice, in each of these cases, there's just a single product. So two smaller things coming together to synthesize a larger product. All right, so let's get into some examples of synthesis reactions. And I want to be pausing the video throughout and bringing in some chemicals and other things. So if it seems kind of choppy and I'm jumping around, that's what's going on, okay? So a very common synthesis reaction, and you've seen this all year long, our good buddy sodium chloride. So what we have going on here is the element sodium being combined with chlorine. Now remember, chlorine is diatomic, so we got a 2 there. And these come together to produce sodium chloride. Now, remember, we've got to balance everything now, okay? We learned that last week, so from this point on, we got to assume everything is going to be balanced. So to do that, 2 chlorine, so I need to put a 2, so 2 sodiums, okay? So that's a synthesis reaction. You got two elements coming together to form a single compound. All right. Another synthesis reaction would be, let's say, the reaction between hydrogen gas, remember it's diatomic, and oxygen, remember that's diatomic. So this is what happens if we burn hydrogen gas. Those gases come together and produce water. There you go. So again, two elements and just a single compound as a product. So if we want to balance this, two oxygens, I'll just have one oxygen, so I need to put a 2 there. Now I've got 4 hydrogens, so I need to put a 2 there. And I apologize for my pen being choppy. All right, so synthesis reaction number 1, first type. Okay, another example, you may have hydrogen combining with, oh, here's a compound, CO2. Hydrogen diatomic. And this produces HCO3, carbonic acid. So there again, we want to balance everything. Actually, I think I'm going to put a 2 oxygens, so I'm going to be 6, going to 6 hydrogen. I'm not sure what's going on there, so don't worry about the balancing on that one. Okay, but this is just an example of a single element in a compound producing a larger compound. So that's a synthesis reaction. Okay. So this next slide here, you have plenty of examples of synthesis reactions where we did water. There's carbon dioxide, carbon monoxide combines with oxygen to form carbon dioxide, formation of ammonia, so on and so forth. So in each of those, notice how there are 2 simpler things that make one more complex compound. Okay, so that is a synthesis reaction. Okay, keep going. Next reaction type, it's called a combustion reaction. Yeah, combustion is when something, boom, explodes, or more specifically when something catches on fire. So with a combustion reaction, one reactant reacts quickly with oxygen. And a combustion reaction is actually a special type of synthesis reaction. You'll see that momentarily. And when we have a combustion reaction, when the product is formed, we always have energy being given off in the form of heat and light. So think about it, if you blow something up or if you catch something on fire, you're going to have heat and light produced. And as always, if you burn something, oxygen has to be one of the reactants. So, but just because oxygen is a reactant, that doesn't necessarily mean it's a combustion. So you think about rust, and that's a reaction called oxidation, and we'll get to that. That's much later. But the key word up here is quickly. Quickly. So something that's rusting, yes, oxygen is a reactant, but that's taking a long time. So the general form of a combustion reaction, we don't really have one. That's because there's a lot of things that combine with oxygen, and the product is going to be different. So we can't just say, oh, element A is going to be combining with O2, and it's going to be AO something, okay, whatever the charge is with A, and that's going to affect the subscript down there. So we don't necessarily have a general form for combustion reactions. We do have a special type of combustion reactions, and that's the combustion of a hydrocarbon. Let's define what a hydrocarbon is. A hydrocarbon is any compound that's made up of entirely carbon and hydrogen atoms. Now, we see these a lot in chemistry as fuel sources. Things like methane, which is CH4, ethane, propane, butane, all of the anes, octane if you're in gasoline. And notice each of those chemical formulas is made up entirely of carbon and hydrogen. Now, these are very energy-rich compounds, which is why we use all of these hydrocarbon derivatives as fuel. We want to burn them. So I'm going to we burn methane in the lab. That's what we use with our Bunsen burners. That's natural gas. So I'm going to burn some here in a second and show you as an example. When we burn a hydrocarbon, there are two reactants or two products rather, that are always produced when a hydrocarbon is being combusted, and that's carbon dioxide and water. So anytime you burn gasoline in your car, that's a hydrocarbon. What's being produced? CO2 and water. You know, you have water that drips out of your exhaust pipe and CO2 that's emitted into the atmosphere, which is one of the drawbacks of burning hydrocarbons is the CO2 emissions. So we do have a general form for a hydrocarbon combustion. Any kind of hydrocarbon that's being burned, you've got to have oxygen as one of the reactants, right? And then the products are always, always, always carbon dioxide and water. Okay, so I got our little friend, the micro burner. You guys know this guy. So in this micro burner, if I can get him flamed up here, I just had him working. Pause that for a second. I'm going to get another one. Pause is not working. All right, so let's try this again. We got our little guy there, our micro burner. Remember him? Okay, so in that micro burner, we have butane, C4H10. So that formula would look like this. So every time we burn that, we've got C4H10. That's reacting with the oxygen in the atmosphere. And the products of a hydrocarbon combustion are always, always, always CO2 and water. Okay? So now, of course, we always have to balance the equation. We can't leave it as it is. So C4, let's try to put a 2 there. We got 10 hydrogens, let's put 5 there and see what this does. Okay, so right now I've got 10 hydrogens. I've got, I should have put a 4 there because of my 4 carbons. So 4 carbons, let's count up our oxygens. Over here we've got 4 times 2, which is 8. And we got 5 over there, so we got an odd number, 13. Remember, I said that if a decimal over here would work, so we need 13 oxygens on this side, so if I put a 6.5 right there, that would technically work, right? Give myself some more space here. If I could put a 6.5 in there, that would give me 13 oxygens, but I can't put 13.5 there. So what I'm going to do is I'm going to put the 6.5 there momentarily and then multiply all the coefficients by 2. So now that would give me 2 there, $13 there, and 8 there. Having to erase everything individually, I apologize. And 10 there. So now I have 8 carbon, 8 carbon. 20 hydrogens, 26 oxygens. So 8 times 2 is 16 there, 10 oxygens for 26 oxygens. So that was a chore, okay? So don't sweat the balancing at this point. Just the hydrocarbon combustion, always the products, CO2 and water, okay? The third reaction type, decomposition. Okay, decomposition is exactly what it says. It's decomposing. So this is essentially the opposite of synthesis reaction. So this is where we've got the breaking down of a larger compound into simpler components, whether it's 2 elements or whether it's 2 or more simpler compounds. And the general form of a decomposition looks like this. You've got a larger compound, AB, and that breaks down into 2 smaller things. Okay. So let's look at some examples of decomposition reaction. The electrolysis of water. Electrolysis is the breaking down of water or anything by an electrical current. Now remember, things that are chemically combined, like compounds, can only be separated through chemical means. Now there's an electrical relationship that's holding the hydrogen and the oxygen together. Remember, chemistry is all about that electrostatic attraction. So in order to break those things apart, we've got to have that electricity that comes in there, something that's not physical. We can't boil oxygen out of water. So we pass an electric current through there, and it splits those things up into the individual components and elements, hydrogen and oxygen. And remember, both of those are diatomic, so they have to exist, H2 and O2. And then to make sure everybody's happy and balanced, we've got to put a 2 there because we have 2 oxygens. Well, now we've got 4 hydrogens, so we've got to put a 2 there to balance that. So it's decomposition. And decomposition is another one of those that it's an easily identifiable reaction because you're moving from a larger thing into 2 smaller things. Okay, so, and it almost looks like a backwards equation because the reactants, it looks like they're going on over here, which technically those would be the products in a decomposition reaction. The products are always on that right side. So you're starting with a larger component over here. Now hydrogen peroxide. The decomposition of hydrogen peroxide. Hydrogen peroxide just naturally decomposes as it's sitting in its container. You guys remember me showing you the container of peroxide that looks like it's kind of swollen a little bit. That's because it's naturally decomposing, and that extra oxygen that doesn't want to be there is being given off. So when that happens, we're left behind with water and oxygen. So as hydrogen peroxide decomposes, it essentially just turns into a more diluted form of itself because oxygen is being given off and water is left behind. So it's just kind of self-diluting as it sits on the shelf. So if we were to balance this equation, a little trickier here, we've got 2 oxygens on this side, and we actually got 3 oxygens on this side. So I'm going to try to put a 2 here and see what happens. So now I've got 4 oxygens total on this right side. I've got 2 over here, so I'm going to put a 2 there. So now I've got to fix my oxygens and 4 hydrogens, everybody's good. So that's decomposition. Okay, so at this point, you might want to pause the video, go back and rewatch, try some of the practice stuff that I'm going to be giving you. So just check your assignments for that. That practice will be there. And now I'm going to start what I'm calling part 2. And I don't think the first part took too long, so I tried to be quick and direct on that. Hopefully, I did that okay. So if you have any questions, please let me know. But moving on, we're going to go to the 4th reaction type. Fourth reaction type is called single replacement reactions, and sometimes you'll hear this called single displacement reactions, so those terms are interchangeable, and I'll often abbreviate it SRR for short, single replacement reaction. So a single replacement reaction, we want to key in on that word replacement. There's something that's being swapped around, and because it's a single replacement, there's only one thing that's being swapped. So a single replacement reaction occurs when a more reactive element forces out a lesser reactive element. Think about it as one element is a bully, it's tougher than the other one, and it's going to kick it out and pair up with what it wants to. Some things we've got to keep in mind when we look at a single replacement reaction is that a metal can only replace hydrogen or another metal, and a nonmetal can only replace a nonmetal. And then we typically find that with the halogens. We use something that's called the activity series to determine if a single replacement reaction can even take place. Because here's the thing, if one of these elements is not more reactive, it can't bully out a lesser reactive element. And this stuff will make sense as we get into this. Our general form is this. Get my marker, my pen ready rather. So our general form is we've got an element A, and it's trying to react with a compound BC. And if the reaction takes place, notice what happens here is A comes in and it kind of boots out B, and B's out here by itself, and then A pairs up with C. And I had it's been years ago, I had a class that there was somebody that said that they always remembered this reaction by, they called it the homewrecker reaction, because in this case element A is coming in and breaking up the happy home of B and this compound BC, and it's kicking B out, and now it's pairing up with C. So let's look at some examples of single replacement reactions, and first I'm going to show you this activity series, and I'll have this for you in your resources. So on the left side of this activity series is your metals, and they are in order, and notice hydrogen is in there also. At the top is your most reactive metal, lithium, and that should make sense because that's one of our alkali metals, right? Lithium, potassium, and then we get calcium, sodium. So these are the most reactive down to the least reactive. So something that is on top can push something out that's below it. Something that is on the bottom cannot push out something that is above it on this activity series. So think of this as like the playground scenario where you've got the pecking order, and lithium is the biggest, baddest guy on the block, and he can beat up anybody that's below him on that pecking order, but anything that's on the bottom here cannot beat up anybody that's higher above it. All right. So those are the metals, including hydrogen. And then on the right side, you've got your nonmetals, your halogen. Fluorine is more reactive than chlorine. Chlorine is more reactive than bromine, and so on. Okay, so now let's look at some very specific examples. And one of these we've already done this year. You guys remember back when we did this reaction where we had the copper wire that we suspended it in the copper, in the silver nitrate, and looked like the fuzzy stuff was on the copper, and then we shook it off, we collected it. Here's that reaction. That was a single replacement, so we had copper that we were adding to silver nitrate. Okay, so those were our reactants. Now what happened was copper came in, and notice over here, copper is higher up than silver on this activity series. So that means that copper, when these two are in an environment together, can come in and push out silver. And that's exactly what happened. Because remember, we collected the silver. That was that fuzzy stuff. That was actual silver. And there it is. We collected that. We funneled it off and filtered it out, right? Okay, so after copper boots out silver, copper then is free to pair up with nitrate. So when that happens, we got to think about that reaction, and copper pairing up with nitrate. It's got a -1 charge. So when that occurs, it's going to be copper NO3 2. Okay, so copper 2 nitrate. And that was what we were left with over here. We had the silver that precipitated out, and then this blue solution was that copper nitrate. Okay, so let's look at some other examples of, oops, need to throw in another slide there. Some other examples of single replacement reactions. I'm just going to come up with some of these on the fly here. Let's say that we have this reaction where we've got lithium metal is reacting with sodium chloride. Okay. First off, we need to ask ourselves, can this reaction even take place? All right. Also, notice one way that we identify this as a single replacement reaction is it's always between an ionic compound. We always have an ionic compound over here, and then something that's trying to replace it. We got a single thing, single replacement, and an ionic compound. So in this scenario, what is likely to happen, or what is possible, is lithium is going to try to come in here and push out sodium. Now remember, a metal can only replace a metal. Now, we need to ask ourselves, can this happen? We've got to go back and look at that activity series. Can that happen? Can lithium, which is up here, push out what was sodium? It's right here. And the answer is yes. Lithium is higher up on that activity series, so it can push it out. So when that reaction takes place, we get the following. Lithium pushes out sodium. And now sodium is out here by itself, and lithium is free to pair up with chlorine. So we come off down to the side, and we have to do that reaction stuff. Lithium has a +1 charge, chlorine has a -1 charge. So when they react, charges cancel, and we've got lithium chloride. And no need to balance anything here, because it's one all the way across the board. One lithium, one chlorine, and so on and so forth. Okay, so let's check this one out. Let's say we've got iron, (3) oxide. Oh, wait, I wrote that in the wrong place. Let's say that we've got copper trying to react with iron 3 oxide. Okay, now what would theoretically push out what? Copper is going to come in here and try to push out this other metal, iron. The question is, can it? So we've got to go back and check our activity series. So can copper, which is right there, push out iron? And the answer is no. Copper is below iron on the activity series. So if we run into a situation where we put copper down in iron oxide, nothing's going to happen. So in this case, we would just put a big NR, which means no reaction. Okay? So that one's easy cheesy. It's not even going to happen. So let's look at some of our halogens. Let's say that we've got bromine, and it's diatomic, remember, it's by itself. Let's say that is trying to react with sodium iodide. Okay. What would be the resulting product over here? Well, we've got to ask ourselves, can this reaction even take place? Now, remember I said that up here a metal was trying to replace another metal. Down here, we've got a non-metal. A non-metal cannot come in here and try to push out sodium because sodium is a metal. what is going to happen is this nonmetal bromine is going to try to push out the other nonmetal. So it's a halogen and a halogen thing. It's the battle of the halogens. So the question is, can bromine push out iodine? So we come over to our activity series and we see that bromine is above iodine. So yes, bromine would push out iodine. So iodine has been pushed out, kicked out of his house, and now he's existing out here. And remember, by himself, he's diatomic. So now bromine is free to partner up with sodium, and when that reaction takes place, we've got sodium with a positive 1 charge reacting with bromine with a negative 1 charge, because it's a halogen, and NaBr. Okay. So those are single replacement reactions. One thing is trying to replace another thing. A metal can only replace a metal or hydrogen. Non-metal can only replace a non-metal, and we have to use that activity series to see if that can happen. Now, that activity series is only used for single replacement reactions, okay? All right, let's move on to the last one, and this is the one that tends to be the most complex out of all the reaction types. We've got a double replacement reaction, or DRR for short. And just as the single replacement reaction meant that one thing was being replaced, double replacement reaction means that two things are being replaced. So in this kind of reaction, we've got ions that swap between ionic compounds. And we've got 3 different types of these, and it's always one of these 3 types. We're always going to have one where a precipitate can be formed, or one where we've got an acid and a base neutralizing each other, and that forms water. Or we might have a double replacement reaction where a gas is produced, okay? So I'm not going to have you necessarily identify these 3 types right now, but just know that in a double replacement reaction, it always results in one of these 3. Okay, general form looks pretty hairy, but I promise it's not. We've got the general form AB. That's a compound AB, which is always an ionic compound. Now remember, double replacement is always between 2 ionic compounds. So we've got AB, which means if that's an ionic compound, this is going to be the cation and this is going to be the anion. And that's going to react with CD, again the cation and the anion, and that's going to result in 2 things swapping places. So think of this as like you're going to a dance and a couple AB comes in, and then there's a couple that's there, CD, and they decide to swap partners for a dance. A pairs up with D and B pairs up with C. Okay, so A will then pair up with D, and that's your cation and your anion, and then A pairs up with D, and then B will then pair up with C, because that's your other positive-negative relationship. So this always helped me here, A, B, and C, D, so that positive will then pair up with that negative, and that's what we got right there. And then this positive will pair up with this negative, so that means I wrote this backwards over here. That should be CB, so that up here should be CB, because the positive always comes first. Okay, so you just have 2 ionic compounds that are swapping the positives and the negatives with each other, okay? All right, so let's look at some examples of double replacement reactions. Television, I've got my goggles on now because we're going to do some mixing here and show you some stuff. So again, this is double replacement. So let's see what happens when we take the compound potassium iodide and we mix it with lead nitrate. All right. So here is potassium iodide. You can see that. It just looks like a clear liquid. Here I'm sorry, that was lead nitrate, just a clear liquid. Here is potassium iodide. It looks kind of like apple juice, maybe. And you guys will recognize this reaction when I mix these two together. It's on the camera. You get, there's our yellow chunky stuff, if you guys remember that. Yeah, you see that on the sides of the beaker there. Yummy. Alright. So what's going on there is we've got this situation. Remember, two things, these are just swapping partners. You've got potassium being the positive component of this compound. Iodine is the negative component. So lead over here is the positive component, and nitrate is the negative component, the anion, the cations and the anions. So this cation will then pair up with this anion, potassium nitrate. Then this, this should be lead 2, so there's a 2 down there. Then the other pair, lead 2, pairs up with iodine, PbI2. So they just literally swap partners. And that yellow chunky stuff that we saw in there is this. So I'm putting a little S right there, and that indicates this is a solid. So we call that a precipitate. And I mentioned earlier that all double replacement reactions are one of 3: precipitate forming, acid-base neutralization, or gas formation. And I'm not going to get into this really, but when we, there's a page for that. When we look at precipitates, the question is, well, how do we know that that was the precipitate? How do we know that that yellow chunky stuff was the lead iodide? Well, we have a handy-dandy chart that tells us. So we were looking at PbI2, which is lead iodide. So we use this chart, we find our cation, oh, there's lead, and we find our anion, oh, there's iodine. So we find where they meet. Lead iodine meets right there. And we got this INSOL, which stands for insoluble down here. And that means that if it's insoluble, that means it's not going to dissolve in water. So it's going to precipitate out, and we're going to see it as a chunky substance. Okay? So if something is SOL, then it is soluble, which means it's going to dissolve, and we're not going to see it as a solid. It's going to be an aqueous solution. So over here, potassium nitrate would have been AQ, aqueous, while lead iodine was the precipitate. Okay. Let's look at one of the acid-base neutralizations. So let's say that we've got our common hydrochloric acid, and we are reacting that with a common base, sodium hydroxide. All right. Now, acids are just aqueous forms of ionic compounds. I'll take my goggles off now, I guess. So here's what happens. In this case, hydrogen is acting as the metal. It's acting as the cation. Chloride is acting as the anion. Sodium is the metal over here. Hydroxide is the negative. So double replacement, so these guys switch partners. The H pairs up with the OH. Look at that, it's H2O. There's water. And then sodium pairs up with chlorine. So anytime we have an acid and a base, when they neutralize, we make water. And an acid is always contains a leading hydrogen there. That's what makes an acid, is the number of hydrogen atoms that it has, protons actually. And a base always has an OH, a hydroxide. And an acid and a base together makes water, H2O. Okay. Let's look at another double replacement reaction. I'm just going to make one up off the top of my head here. Let's say we have calcium phosphate. It's going to be PO4, 3 negative charge, so the 3 comes down there. Calcium has a positive 2 charge, so it comes down there. And that reacts with, let's go with magnesium carbonate. So magnesium positive 2, carbonate negative 2, so they cancel out. What's going to be the resulting products? So here's our 2 ionic compounds, double replacement, so they're going to swap partners. Calcium is going to pair up with carbonate. Calcium positive 2, carbonate negative 2, so they just cancel out. Magnesium pairs up with phosphate. Magnesium has a positive 2 charge. Phosphate has a negative 3 charge. So when they combine, crisscross Mg3 PO4 in parentheses with a 2. Then after all of that is said and done, you could go back and, I'm going to get my eraser. If we want to be very precise, we can go back and balance that guy. You guys have the ability to do that, hopefully. If not, we'll work on it. So remember, if we have ionic compounds or polyatomic, like phosphates and carbonates, think of them as a single group. So let's just pick something to fix. 3 calciums, 3 calciums. So now that means I've got 3 carbonate groups over here. So I need to fix that. So we'll put a 3 over here to fix my carbonates. So now I've got 3 carbonates. So that 3 in front of my magnesium tells me I need 3 magnesiums. Oh, I got 3. Okay, how many phosphate groups? I got 2 phosphates over there, 2 phosphates over there. Yay, everything is balanced. Okay, so I'm going to stop there. I'm going to give you guys a list of other videos on the internet that just give different approaches to these reactions. There are tons of resources on the internet. YouTube videos out the wazoo of people showing you the reaction types. So and it typically takes 2 or 3 goes at this before things start to click. Some people just pick it up and run with it, and hopefully that's the case with everybody. But don't be intimidated by this stuff, okay? Just take it one step at a time. Touch base with me. I'm going to give you a lot of practice over this stuff, over the reaction types, and I don't want you to be intimidated. Right now, more than ever, communication is key. So just stay in constant communication with me if you have problems, and we'll address those as we come to them. So I want to stop here and hope you guys are safe. Everybody stay positive. Everything is going to be just fine. We're going to get through this, and we'll come out better and stronger on the other end. Love you guys. Let me know if you need anything. All right, see you.